This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Planes. All right, so that was that, but is there any other question you'd like to ask me? Anybody? Yes?
For the energy equation.
Energy equation, yes.
In the right-hand side, so when we have the Bashar-Walk, and if we assume
Inviscid flow.
Is it always that true that only we have Bashar-Walk, or we might have some case?
It's not virtual work, it's the actual work that's done by the pressure force. And that's accommodated by including it in the enthalpy.
So if I bring it in the left-hand side, I can put 0 in the right-hand side? Yes, the energy equation will have, if you have the enthalpy, in general, the energy equation is the rate of change of energy in the volume plus the net flux out is equal to the work done on the boundary. And it does not include then the pressure forces because they're included in the enthalpy. And the rate of change of energy in the volume is rho into E, the internal energy per unit mass, plus a half U squared, the kinetic energy, plus the potential energy if there were some. So it's the integral over that, and it's the rate of change of energy in the volume. So it's ddt of the integral over the volume of rho times the energy per unit mass, and rho dV is an element of mass dm. So dm times the energy per unit mass is the amount of energy in a mass dm, and I'm simply going to sum all of that over the volume, and then look at the rate of change of that in the volume. And the rate of change of energy in the volume is equal plus the net flux out of the volume. So that is H, if you include H, because you include the pressure work, H plus a half U squared times rho U dot N ds. And U dot N represents the mass flux in the normal direction. The component of the mass flux across the surface area ds ends in the normal direction, so it's not just rho U ds, it's got to be the component normal to the surface, so it's rho U dot N ds. Yes. So if I want to keep the Bashar-Walk at the right-hand side,
yes,
I have to put minus.
And well, then you'd have to keep the pressure work on the other side, yes, and you have to be careful about the signs, because the conservation law. Where did I do that? Conservation law is very early on, I think.
I think it's 4 or 5.
5, is it? Yes. Yes, so here's what I did. So this was using Gauss's theorem, and that was the momentum equation, and then that led to this idea that the force on the ith direction over the normal n depends on these other directions, and I worked that out for you. And concluded that pi I, or the I, that's the component of the stress in the ith direction on the normal n, is equal to pi ki nk. So I can always work that out by calculating locally the stresses that act on normal planes with respect to the plane of my surface. And now when I came then a little later, so this was Gauss's theorem. and conservation of energy. So here it is. So the first part on the left-hand side is the rate of change of energy following a moving volume, moving with a set of particles. And that's equal to the heat, the external heating, and the stress tensor, and the work done by the stress on U, and it's the, if there's an external body force, then that might be the gravitational force, and that does work as well. So that's the full equation, and then, so this is where I worked it out for you, and I really used the Reynolds transport theorem to get from the moving volume to a fixed volume. And there it is there, that's the rate of change of energy in the volume, plus the flux of energy, so that UK is simply U dot N. You know, it's N has components N1, N2, N3. And so U dot N is UX times NX plus UY times NY plus UZ times NZ. That's U dot N, or U dot N cos theta. The magnitude of U times the magnitude of N times the cosine of the angle between them. And that's something you know from what's meant by U dot N. And then this is the work done by the stress tensor. And the stress tensor, so if there's a conservative force, I put that in here, and we can, with a little bit of subtlety, so long as the potential energy doesn't depend on time, then we can include that on the left-hand side. And then this part of the stress tensor is minus P delta Ki times Ui, which summing over I means that delta Ki is always 0 unless I is equal to K. So if I have I equal to K, then I get one, there's only one component here, so this will be minus PUK. And so that rho UK becomes minus PUK, and so I can include that in with the energy, internal energy E. And so I have E, which is H plus P over rho, right? So if that H is E plus P over rho, and I multiply that by a rho, I get just P, and I have therefore PUK on the left-hand side, which is, so I've included the work done by the normal force, the pressure on the boundary, not by the viscous stresses on the boundary. Right? And so they're still here in this tau Ki. I kept pi Ki is tau Ki plus P delta Ki. The total stress. And when I've written pi Ki, because there's a pressure force on it as well as a viscous stress on it. All right, so that's the first question. Now, are there any others? I should say, I mean, if some of you are not familiar with tensor notation, it's a wonderful notation. I only use it for Cartesian tensors, namely x, y, and z, as when I have I don't use it for curvilinear coordinate systems because it's complicated and I need
Schwarz-Christoffel transformation, and it gets very messy. So I don't do that. But because it works with vectors, vectors don't depend on the orientation of the coordinate system. I can always have a step in space, which is a vector, step in space, and it doesn't matter which coordinate system I have. So I write my equations in terms of stresses and forces. Forces are vectors. And then I needed to be a little careful because my force on a surface of normal n can always be decomposed into forces on the three normal areas intersected by that principal surface. Is that clear? And then, as I say, I find it a very helpful notation because it becomes very simple. All I have to do is sum over the coordinate that's repeated. Okay, is there anything else? Yes, good.
I was going to ask what actually it sort of means by, like, you said there's like three forces. There's the heat force and the pressure force, and then there's like a stress.
No, there's not a heat force. There's a heat flux. So so let's go back to this equation. So here was the general equation. So I had the rate of change of energy in the volume, and what can change it is heating will change it, or work done on the boundary that I get from the first law of thermodynamics. So this is just a statement of the first law of thermodynamics, and so I could be talking about external heating. For example, it could arise from the fact that I'm burning a fuel, and that's adding heat, as if my gas was not the fuel plus air, but it was a working fluid, say just nitrogen. But I can imagine what happens when I burn the fuel in oxygen in the air by imagining that I have just added heat to the flow, as if it were all nitrogen.
What about that second term? You said was stress term.
So this is that's a stress term. So it's a force per unit area, right? So it's a force per unit area. So it's like a step in space. It's a vector, but it does work, and you've got to be sure that you'll get the work done on the fluid, and so that is pi on the surface n multiplied by the velocity, or the component of the velocity, dot u. So it's the component of u in the direction of the force that does work. If there's a component of u that's perpendicular to the force, it doesn't do any work.
It's like stress within the fluid.
It stresses within the fluid. And there are two. There's the pressure and the viscous stress. And it's helpful to treat the viscous stress separately, often helpful because it's often negligible. At high Reynolds number, it tends to be negligible. If I was talking about honey, I'd have to include it for sure. If this was honey on porridge and I'm heating up the honey, and then you'd better be careful. But this is the right equation. Always the right equation. This is the energy equation. And you're talking with people who are not had the advantages you've had if you're in some company and they don't know this. You have to know it as if you could tell me what it is standing on your hands. 2 a.m. in the morning. you have to be able to tell me what is conservation of momentum, and what is conservation of energy, and what is conservation of mass. If you don't know that, you're not going to be helpful to anybody in industry, I can tell you. I can tell you. From lots of experience. Lots of experience. Yes?
So with the conservation of momentum, with
Yes.
the body forces term,
Yes.
we're usually neglecting that, or we assume that it's negligible. When is it not? What's an example of a case where you can't neglect body forces?
In the momentum equation, you always have to include it. The only time when it gets complicated is if the body force is changing with time. In other words, it's not minus g per unit mass, but g is changing with time. Now, if you were doing astrophysics, that would be the case. And you are not going to get the right answer in astrophysics.
Is that important for rocket design?
No. No.
Changing enough?
No, it's not changing at all. G's not changing at all. So I could... are you in space? Are you...
When you're moving to space.
When you're moving to space, no, G's not changing. I mean, it's negligibly small. You might be flying over Iron Knob. Might change a bit if you're flying over Iron Knob. Before they mined it all. Anything else? What else would you like to know? Nothing. Good. Well. Yes.
Maybe in lecture 12.
Yes.
When we discussed how can we measure the velocity and when we have supersonic flow. In lecture 12.
Ah, yes. Which tab?
This one.
Ah, there we are, lecture 12. Yes, thank you.
You go scroll down.
Scroll down, yes.
Yeah, this application.
Oh, yes, yes, yes. Oh, yes, 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 the pitot tube. So, now what is it about that you'd like me to clarify?
When you have Mach number supersonic flow, how can we measure? When you say the total temperature, and we have to measure the total temperature to get the velocity.
Yes. Yes, so why? Well, the fundamental reason is that the total pressure here, oh, that's not clear. This total pressure is not the total pressure here before the shock. The total pressure changes through the shock, goes down. So that's very important to know. However, locally here, the flow is, after this shock wave, is going to be essentially isentropic. So the relationship between the total pressure here and the static pressure outside, somewhere away, is Pt over P is 1 plus gamma minus 1 over 2 m squared to the gamma over gamma minus 1, where P is the static pressure at Mach number m. Right? So if I measure Pt prime and P, I can get the Mach number from this relationship, where P is the static pressure, as if that probe were not there. And it's easy to measure static pressure, relatively, harder to measure the total pressure. However, that's the idea. So if I measure this total pressure here and the static pressure downstream, and I showed you the kind of probe that's used to measure the static pressure down here, then the ratio is 1 plus gamma minus 1 over 2 m squared to the gamma over gamma minus 1. So that's a perfect gas. P is rho to the gamma. And so you have it. Now, so measuring PT prime and P, you get the Mach number. But now, what I want to do is get the if I can measure the total temperature here, if I could measure the total temperature, then the total temperature divided by the static temperature, which would be AT squared over A squared, will be 1 plus gamma minus 1 over 2 m squared. That's a consequence of conservation of enthalpy.
This M is after the shock, right?
This is after the shock. This is, this is as if the shock were not there. As if the shock were not there. It's the static pressure that would have existed if the shock were not there. So M is the Mach number of the flow. So it'll be far downstream if the shock is there and you have an actual probe in there like that. And that tells you then, if I know this total temperature and I know the Mach number from this relationship, I get T or A. And if I know A and I know the Mach number, then I know U. So that's how it works.
For the subsonic, we don't need to measure A because it's the same.
No, we don't. Subsonic flow,
I think it's up.
oh yes. So in subsonic flow, m less than 1, I have this kind of probe, and I can measure the total pressure, and I can measure the static pressure.
And I can assume A doesn't change.
And I can assume that A naught doesn't change. So I know the Mach number, therefore I know the pressure, I know everything.
Question for this. So if we assume, let's say we measure supersonic flow.
Yes?
But in this case, aren't we just measuring something after the shock? We're measuring the
Total pressure.
Okay. But that's going to change across the shock.
Well, no. The total, yes, it is going to change across the shock, but if you're right on the center line, then it's a normal shock. And we're assuming it's a normal shock. So it's a normal shock that you have to bring the fluid to rest behind that shock wave. I want to keep the fluid on the axis so it doesn't go anywhere else. So I need my total pressure probe to be lined up with the stream direction, maximizing that total pressure. Yeah. Anything else? That's a good question. Anything else? Yes.
Did you just say that the total pressure doesn't change if you're on the center line?
No, that's not what I said. Well, it doesn't change after the shock. From after the shock up, the shock gives rise to an entropy change. And that entropy change is proportional to delta P over P cubed. And I was at pains to work that out for you. And that comes from the shock Hugonio. If I write the equations for a shock wave, a discontinuity, I got the shock Hugonio, or the shock adiabat, and that gave me the connection between the pressures across it and the density across it. Everything else I want to know about the flow upstream and downstream of a normal shock. And I used that normal shock relationship finally to get what I have for an oblique shock. I had the flow at an angle beta, and so I could always add this tangential velocity v for the oblique shock. So now this flow here, I have a shock wave that changes the total pressure. But from here on, the flow is regarded as isentropic. And it will be unless there's heat that's being supplied. Or there's a massive amount of work done by viscous stresses. So you'd have to be slightly careful. But if it's just reversible flow, then this is isentropic from here to here. And that total pressure will relate to the Mach number.
So is that shock created just from the pitot tube?
Yes. Yes.
So does that mean that the pressure that's measured from the pitot tube is effectively not completely accurate?
I know it's accurate. It is the total pressure behind the normal shock. So that's a good point. It's the total pressure behind the normal shock. So it's PT prime. It's the total pressure behind this shock wave. And it's on the axis. So it's accurate. The total temperature, which is the temperature I would measure if I brought the fluid to rest right here. And that is a little subtle because you can imagine that if I had a high heat transfer away from it, then the total temperature would be changing from the energy equation. Yeah.
Excuse me, another question. If I want to calculate the thrust while I have a oblique shock at the exit of the nozzle, and I want to simplify the problem, so I want to use the Mach at the exit where I have isentropic relationship before the shock. How far is this assumption true? Because I calculate thrust based on this Mach exit, but I ignored the oblique shock effect. How far this assumption is true?
Now, it would depend on whether the pressure at the exit is higher or lower than atmospheric pressure. So if atmospheric pressure is low, then when the flow is supersonic and comes to the end of the rocket nozzle, it needs to expand. So it turns, so there'll be no shock wave. I'll have an expansion fan. And then, of course, I have to turn the flow back subsequently, so there's a shock well downstream. If the pressure outside is higher than the pressure at the exit, then I could easily have either an oblique shock or a normal shock at the exit, or that normal shock at the exit could migrate upstream. And I have a complicated flow inside the rocket nozzle. The simplest idea would be that it's a normal shock,
but it may not be. It may be much more complicated. There's boundary layers that separate, and it's the flow gets turned ahead of the shock wave, and there's complications.
So if I have overexpand flow, then this assumption is not really true.
If I have an overexpanded flow, so that the pressure is lower than the outside pressure, then I have to have some sort of shock structure. And it may be that I can match the pressures through an oblique wave. And I have an oblique shock. So I could have an oblique shock at the exit, but I don't need that if I'm going to calculate the thrust of the rocket nozzle. I can do that right at the exit of the nozzle. And the thickness of the shock there is negligibly small.
But they have to include the partial difference, right?
No. If I had a plane right through the nozzle, I know what the pressure is, because that's all supersonic flow, so I'd use that pressure. But I'd have to be a bit careful now, because depending on this control volume, I've got an outside pressure that's not the same all the way around the body. I have an upstream pressure, but I downstream through the exit area, I have a different pressure. So I better be careful for the whole volume. So I could draw my control volume. So here's my rocket, and I can draw a control volume that is arbitrarily large, but I have an AE where the pressure is something, and the rest of it, A minus AE, is atmospheric pressure, assumed. Whereas upstream, I have the full area A, and the forces acting in the direction of the flow. That's the direction of the force. On the other one, the direction of the force is upstream. Minus P dot N. Anything else? So that's a good question. So I do urge you to know some things really pretty well, because I have had in mind that you're going to leave here with a stamp on your forehead, and it's going to say Melbourne University, Mechanical Engineering, and therefore you're going to be presumed to know something. And it will be to my eternal embarrassment if you don't. So I do hope you've paid attention to some of these things and really taken them for real, because you could easily find yourself in a consulting situation where people are going to turn to you and say, what's going on here? And if you're like everybody else who throws their hands up and has no idea, then everybody's in trouble, and you may lose your job. So, all right, what else do you want to know? Anything else? Yes?
Any advice for the exam?
Yes. Do some work between now and then. Think hard, because you should have come today with the questions that you can't answer. What is it that I have done that is not self-evident, not clear? I certainly tried to make everything I said clear. And if it's not, well, that could be that I've assumed that you know more than you know. That could easily be true. Easily true. What else? Yes?
Lecture 14, we talk about the reflection in a closed piston. Closed piston, the wave reflection.
Oh, reflection? Yeah, yes.
I think it's easy to consider that in a closed piston, the shock wave will reflect. But how about the open end piston? Why there is a reflect?
Why is there a reflection? So this was the piston problem, small piston motion, and this was a case that we could work out, right? So here was the piston moving at the velocity up. So on this xt diagram, it has a line that looks like that. It's changing, it's a straight line on the xt diagram. And here, the pressure behind, here's the weak shock going out ahead, and here's the gas that's not moving at all, and here's the pressure P1, right? So the pressure behind that shock is higher than P0, than P1, I'm sorry, higher than P1. It's P1 plus delta P. And delta P was rho A UP, right? So it's higher. Now, what happens when this weak shock wave comes to the end of the pipe? So if it's a closed end, it's obvious. It's a closed end, the velocity has to go to 0. So you have to reflect the wave back. And so your question is, what happens if it's an open end? And so, well, you think about that. If it's an open end, the pressure is going to be atmospheric pressure P1. But the flow coming out is not at that pressure. The pressure is higher. It's delta P higher. So the boundary condition at that point now is a boundary condition not so much on the velocity but on the pressure. And it's an approximation that the pressure can't adjust through an expansion wave. This is not a supersonic flow. The flow is only moving here at the velocity up. U2 is equal to up. So it's highly subsonic flow. So a highly subsonic flow, the flow is going to be accelerated by the pressure gradient, and that's going to drop the pressure. So the pressure at the exit, to a first approximation, the pressure at the exit is atmospheric pressure. If it were not, you'd have an acceleration of the flow away from it until it was. No? So it's a boundary condition. It's a boundary condition on the pressure. And that is, so you have to have another wave, and you need a wave that goes back. And I think I worked that out at the time. No, this was all about shock waves. It's in the next lecture. So, okay. I think it could be in here. Oh, no, this was where I was playing around with the acoustic approximation. It's a wave, and this was the method of characteristics for that case. Oh, and here's an example, a reflection from a closed end, and then I did the reflection from an open end, reflection from an open end. And so at 3, I am assuming that the pressure is P0. And then on this characteristic here, C1 plus P minus
P naught plus rho naught A naught U is 2 rho naught A naught UP. P3 is equal to P naught, so U3 is equal to 2 UP. So I can get on the characteristic going back, I can find what the constant is. So that was the idea. So now I'm not really expecting you to have fully understood the method of characteristics. But it would be very disappointing to me if you had not the foggiest clue what it's about. It's vital to compressible flows. This is a time-dependent compressible flow, a one-dimensional XT kind of problem. And I talked last time, not for exam, about the method of characteristics in 2 dimensions in a steady flow. And what happens if you have a rocket nozzle and you had to design the rocket nozzle for some external Mach number, or you had to design a supersonic wind tunnel to have some test section Mach number. Yes? Anything else?
Yep. What actually happens to the fluid particles when a shock occurs?
Ah, that's a good question. This shock is a discontinuous solution of the equations. So you don't actually have to work out what's going on inside the shock. But people have. And Graham Bird at Sydney University made a living for a lifetime out of working out what's going on inside a shock wave. And it'll be subtle. If I change the gas to a mixture of a monatomic and diatomic gas, it'll be complicated. And so, and the shock wave in reality is about 3 mean free paths thick. So, since it's only 3 mean free paths, it's hard to use a continuum approximation, even for the stresses. So he had a Monte Carlo method for doing it, keeping track of individual molecular collisions. So there's a Monte Carlo method that keeps track of individual molecular collisions and then adds them all up and statistically arrives at what happens and how the density jumps from one value to another value, how the pressure jumps from one value to another value, and so on. What is the internal flux of heat? But even the idea of heat, that Q, Fourier's law is Q is minus K dt dy or dt dx. That's a continuum approximation that won't work well if you're talking about mean free paths that are and distances that are of the order of a couple of mean free paths. So you'll have to have a different method, and he did it by molecular collision method, a Monte Carlo molecular collision method. But that's approximately what is known and why so much work has gone into shock tubes. Big program at Caltech for years and years, looking at the structure of a shock wave. But you don't need it if you're interested in the N wave from a Concorde. It's not going to be affected by the internal structure of the shock wave. It's a discontinuous solution. Yes? Good. Anything else? Nothing else?
You've mentioned before that you can kind of choose whether you want a weak or a strong shock wave.
Yes, good idea.
How do you physically set it up so that you get either one? Is there a way to do that?
I mentioned it in the context of
an attached shock and a detached shock. And that's not the only circumstance in which you can get some difficulties. So in the flow that I spoke about, where it was a two-dimensional flow, I had a center line and I turned the flow down. Well, there's a solution for that, which would be an oblique shock wave, and the flow is supersonic coming in and supersonic coming out. And everywhere the flow coming out, if it's been through that single shock, everywhere the flow has turned the same angle. So it's compatible with a solution that has a wall like that. So that's an attached shock. And so in thinking about flow fields for bodies, it's useful sometimes to imagine a flow field with an oblique shock, for example, and then to say, well, what would be a streamline? And I can replace the streamline by a body, and that is then therefore going to satisfy the boundary condition, that the velocity is parallel to the surface right here and parallel to the surface up here. So I've satisfied the boundary conditions, I have a solution. But what if I keep increasing that angle? What will happen? You tell me. I increase, here my plate downstream is hinged here, and I'm going to deflect it a little bit. Then I'm going to deflect it some more. And then some more. What? Beg your pardon?
It'll detach?
Correct. You'll go from the weak solution, which is the supersonic flow downstream, to a strong solution, and you'll probably get subsonic flow. And the most likely subsonic flow is somewhere a normal shock, just by the symmetry of the problem. Now, that may not be the case. You may be able to have a very long body and there's some high angle down here, and you put some sort of oblique shock wave, which is so strong that it satisfies the boundary conditions for the problem. But that's a hard problem. Once the flow is subsonic, it's a hard problem.
So it's preferred to keep it supersonic then?
Well, the trouble with keeping it supersonic, well, it's a two-edged sword. If you keep it supersonic, then you're going to want to have weak shock waves. Because the stronger the shock, the more the entropy is going to be lost and the higher the drag. Right? So now you've got to be there. You know, real engineering has real compromises here. You know, I have a wing that has got to carry a bending moment, and maybe I've got to have a rounded leading edge. Maybe I can't make a sharp leading edge, or maybe I don't want a sharp leading edge because this aircraft's got to take off and land subsonically. So typically, it'll probably have a rounded leading edge.
So that's for the subsonic flow?
That's the subsonic flow, but then when the aircraft's flying supersonically, unless the wing is oblique to the flow, and then I'm taking a normal component, which may be subsonic, but if it's not, if it were perpendicular to the flow, then I have no supersonic flow solution. Why? Because if I had a supersonic flow, I know that if it were one-dimensional and I'm coming along here and I have the fluid has to come to rest at that body somewhere, has to come to rest, it's going to have to diverge. But if it diverges in a supersonic flow, it accelerates. So that's obviously incompatible. The only way you can have an accelerating flow, a decelerating flow that's expanding in area, is if it's subsonic. So you have to go through a normal shock. But the normal shock gets weakened quickly by the reflected characteristics. As you go around this corner, you have characteristics that weaken the shock. So the shock gets weaker and weaker until you finally get right away, instead of the shock being normal, the weakest shock is when it's at an angle beta, or mu rather, mu to the free stream velocity. So it's a Mach wave, but it doesn't go away. Anything else? So I'm here captive for as long as you want. Not for much longer, only another 5. So anything you want to know? Yes?
Like, if you're not talking about like a man-made physical surface or something, say the wind's just blowing, and then a shock is caused in the wind, like what could physically represent that?
An explosion. So if I have an atomic explosion, it is monumental. That shock wave was monumentally strong. Took the roof off that observatory or whatever it was in Hiroshima. And if you haven't seen it, all of you need to see it in your lifetimes. It will be a life-changing event. Much like seeing a concentration camp for the first time. You can't quite believe that it happened. You can't quite believe that it happened. So you have to go. Any of you from Japan here? No? No. Any of you been to Hiroshima? Any of you? Not one. Okay, well, mark it down. You've got a long time to go. But you need to see it. So, yes, an explosion will create a shock wave. Other natural phenomena, a volcano could create a shock wave. Some huge eruption. Beg your pardon? Thunder may be a shock wave, but it's a very weak wave. It's an acoustic wave, but it's probably at its source a shock wave because its lightning is suddenly heated. So if you take a volume of fluid and you heat it, the pressure goes up. So in terms of our one-dimensional motion, that rising pressure is going to propagate away acoustically, and it'll probably propagate away as a shock wave. Yes. Yes. Anything else? Well, I hope you do very well on this exam. I'm going to be mortified if I think that you don't know the answer to the very first question that I've asked. I'll be mortified. I will. It's a judgment of me rather than of you. If you don't, so I encourage you to actually read what I wrote. And if it remains incomprehensible, you better contact me. You can do that by email. Contact Morgan, she'll tell you the answer. And if she doesn't know, she can contact me. And I'm very happy to explain it one more time. No trouble at all. But you do need to, there's nothing that I did that is not, in my mind, important, relevant. Relevant to understanding something, never mind actually doing something, but at least you can't do anything much unless you understand what you're doing. That's my experience. Okay, we quit. Good luck.
Thank you. Thank you.